4 basic functions. What I'm actually going to be doing here is a series of 3 videos discussing 12 basic functions, 4 functions per video. There are many families of functions. Considering the following 4 parent functions. Parent functions are going to be the simplest form of a family of functions. Do they have continuity? What is the domain and range? And are there extrema? Are there asymptotes or other defining features in the graphs? So as we go through these 12 basic functions or these 12 parent functions, we're just going to be identifying anything that is noteworthy about those functions. All right. For our first function, we're going to look at the identity function, which is simply f of x is equal to x. You might also see it as y equals x, but as a function notation, we would use f of x equals x. Now, you may also refer to this as a linear function. The reason that we call it an identity function is because if we did look at this as y equals x, then it tells us for every x that we plug in there, the y value is exactly the same thing as the x. In mathematics, an identity means that something is the same as itself. All right, interesting fact about this. This is the only function that acts on every real number by leaving it alone, right? Whatever value you plug in for x, you're going to get back the same value as y, because the function is really just y equals x. All right, does this function have continuity? Yes, it does. It's a straight line that heads in this positive direction. I call it the perfect diagonal. It's at a 45-degree angle. The slope is up 1 over 1, and it does cover all possible x values. Okay, there are no x values that this would be undefined for, or there's no reason to have any breaks or asymptotes in the graph at values. So continuity? Yes, it does. The domain is going to be all real numbers. The range is identical to the domain. It's going to be all real numbers, and an interval notation would also be negative infinity to infinity. Okay, is this function even, odd, or neither? For even, it must be symmetric about the y-axis. That means we should be able to reflect it over here, which it clearly does not. You've got a top part in quadrant 1, but you don't have anything in quadrant 2. So not an even function. An odd function needs to have a point of symmetry at the origin in such a way that you could choose any point along the graph, match it up with that origin, and then identify another point on the other end of it. The point of symmetry of the origin would always be a midpoint between 2 other points. All right, so if we take a look at the graph, it does go through the origin, which is not a requirement to this being odd, okay? But we are going through the origin. And if I picked out a point that was on this side over here, let's just go ahead and take 3, 3. If I take that point, is there another point that's equidistant from this point to 3, 3 in the opposite direction? And there is. We just move that direction and we got negative 3, negative 3. Okay? The point of symmetry will always be a midpoint to 2 other points that are on the graph. And that's the case that we do have here. So this is an odd function. For our second function, we're going to look at the squaring function. Okay, and that would be f of x is equal to x squared. This is also called a quadratic function. An interesting fact about it, the shape of this function is called a parabola. That I hope you already know, okay? But it has a property that's useful for making flashlights and satellite dishes. That is something we'll definitely revisit when we study another unit called conic sections. In conic sections, we do talk about the parabolas and some other shapes that are somewhat similar to this one. All right, does this function have continuity? The answer is yes. It does. It does not have any breaks. There's no reason for any breaks in here. If we look at what the function is, which is just to square a number, there does not exist an x value that you can't square. You can square positives, you can square negatives, you can square fractional numbers, you can square 0. There is no reason that this function would not accept an x value, so it does have continuity. The domain here is also going to be all real numbers. Okay, negative infinity to infinity. The range is not going to be all real numbers. The shape of this graph has a vertex over here, has a vertex at the origin. Okay, so the graph will extend upward forever. It is not bounded above, but it is bounded below. It is bounded below at the x-axis or at 0. So the range is going to be a closed interval at 0, and that goes up to infinity. We're going to use a closed interval because it does exist at 0. It does make it to that point. Does it have an extrema? Yes. If the range is bounded in any spot, it does have an extrema. That extrema here is going to be at that vertex at 0, 0. Okay, so it's going to be yes, and that is going to be at the origin 0, 0. Is the function even, odd, or neither? This function is even. It is reflective. It is symmetric about the y-axis. The right side looks identical to the left side around the y-axis. This is even. Now, as a little bit of advice, but don't rely on this completely, because we've got to be careful when we get into transformations of functions. This is an even function, and we are seeing x to the second power, and the second power is an even number. If you go back to example 1, f of x equals x, that can be interpreted as f of x is equal to x to the first power. And the first power, or 1, is an odd number. Okay, now do not rely heavily on just seeing those things, because once we begin some transformations, then things can change. Then things can be different. Our third function is going to be the cubing function. F of x is equal to x cubed. So far, what we've been looking at is taking x and raising it to the first power, the second power, then the third power. Okay? We also just refer to this as a cubic function. Interesting fact. The origin is called a point of inflection. This point here is a point of inflection because the graph changes curvature at that point. Okay, what that means is that as you follow the graph, say from this side here, it begins to curve in this direction, begins to curve into the x-axis. Once you get to that point, it then switches its curvature away. Okay, you're curving into it almost like it's a parabola that's going to come back down, but instead of moving in that direction, it switches and then begins to curve in an upward direction. That point is called a point of inflection. Does it have continuity? Yes. There does not exist a value for x that you could not put into this function. There are no reasons for breaks, no holes or asymptotes in this. Continuity, yes. The domain is going to be all real numbers. You can plug any x you want into this function. There's not a restriction on what you can cube. The range is also going to be all real numbers. Okay, it does extend down forever. It does extend up forever. The larger negative number you put in, the larger negative number you're going to get out. There's not a bound to that. Okay, even, odd, or neither. We did look at this one previously. This function is going to be odd. We do have a point of symmetry here. You could grab any point on the graph, line it up. You can grab any point on the graph, line it up with the point of symmetry, and identify another point that is equidistant from it on the opposite side of that point of symmetry. So this is going to be an odd function. And again, make note here that this is x to the third power, and 3 is an odd number. Of course, when we start doing some transformations, things can move around. That point of symmetry might not be at the origin, which is a requirement to being an odd function. So don't rely too much on what you see as the exponents, but there is definitely something there. All right, for our fourth function, we're going to be looking at the square root function. F of x is equal to the square root of x. You're going to notice that I didn't continue along the trend of the other ones. We did not look at f of x is equal to x to the fourth power. But just as a note, f of x to the fourth power will be an even function. F of x to the fifth power will be an odd function, and so on. And again, be cautious of any transformations that may change some things in there, but as their parent function forms, they would alternate between even and odd and even and odd, starting with x to the first power is an odd. But as a side note, with respect to exponents, the square root of x is actually x to the 1/2 power. It actually is x to the 1/2 power. Okay, we're not going to pay too much attention to that right now, but that is a true fact. Another interesting fact, if you take the square root of a number, then take the square root of that answer, and take the square root again and again and again and so on, eventually the answer is going to get very, very close to 1. It basically becomes 1. And let me demonstrate that to you real quick. Let's just take any number. We'll start with 800. Nice big number. All right, so the square root of 800 is that. What I'm going to do is type in the square root of my last answer so that way I can continue just to hit enter over and over and over again. So it already drops down to 5.3. And I just keep going and going, and you'll begin to see that it starts to settle off at 1. You've always got that little bit at the end. Look at that. Eventually the calculator even tells you it's just 1. All right, so continuity. Here's a picture of the graph that we've got. It does appear to be continuous. It is going to be continuous, that is true. It's only going to be continuous for where the graph is actually defined. So as a function, you can't plug in any negative numbers. Okay, you cannot take the square root of a negative number and get a real value, which means that we can't graph it. Okay, you can plug in a 0. The square root of 0 is 0. So you get a point here, but nothing exists to the right. Okay, as far as the domain, what that would mean is that we're bounded at 0. Okay, it starts at 0 and goes to infinity. But along the part of the domain that we have, from 0 to infinity, it is continuous. There don't exist positive numbers that you can't plug into this function and take a square root. So continuity, yes. Even though it doesn't cover all real numbers for the domain, for what it does have continuity. The range is also going to be bounded. Coincidentally, it is the same thing as the domain. It's going to be bounded at 0, and it's going to go to infinity. Okay, now the domain is measuring to the right. The range is measuring up. So we start at a low point of 0, and the graph continues to go up. It doesn't go up that fast. It doesn't go up that fast, but it is always increasing. Okay, the larger number that you plug in, the larger square root that you're going to get back. So it is going to continue to get higher. Does it have an extrema? Yes, it does. It has a minimum, and that is going to be at 0, 0. And I should make note that in example 2, I identified that it did have an extrema, but I did not state that it was a minimum. Okay, so in example 2, with the parabola, the x squared function, that did have a minimum at 0, 0. Is this function even, odd, or neither? Well, nothing exists over here, so it can't be even. Odd, if I choose any point along the graph, there's not going to be a point over here that matches it. So this will be neither.
Later, blah.